In Chapter 2, we deal with our first partial differential equation, the heat or diffusion equation. The one-dimensional form is u sub t equals d uxx, where d is the diffusion coefficient. Then you can have convection terms where v is a wind or current velocity, then the reaction term and a source term, but mainly we'll be interested in the diffusion term. So this is a one-dimensional problem. The solution can represent temperature or concentration of something that's diffusing. The solution is going to be a function of t and x, so it's a partial differential equation. It depends on time and x. So this could be diffusion or heat conduction in a wire or a rod. We'll assume that we have the temperature is given on both ends for all time and given at t equals 0 for all x. That's typical initial conditions for the heat equation. So we'll start by using the most obvious finite difference approximation to that. We approximate u sub t by u of xi tk plus 1 minus u of xi tk over delta t. That's just the Euler approximation to u sub t with the xi fixed. Then on the right-hand side, we use the usual second-order approximation to the second derivative, u of xi plus 1 minus 2u of xi plus u xi minus 1, all at tk over delta x squared. That's just approximation to the second derivative of u with respect to x. And then we also approximate the first-order derivative term with centered differences. This is called an explicit method because we can explicitly solve it for u of xi tk plus 1. Now, notice there were no tk plus 1s on the right-hand side, so it's an explicit method. So we can solve for u at xi tk plus 1 in terms of the solution at the previous time step. So we have a stencil represented by this diagram here. The circles represent known values. These are the initial conditions. The solution, let's call it temperature, is known at t equals 0 for all x. It's known for all t at the left-hand point and the right-hand point. And the stencil shows that shows which unknowns are related. U xi tk plus 1 is given in terms of u xi minus 1 tk, u xi tk, u xi plus 1 tk. It's explicit because we can solve for this. So we can solve for this in terms of these three, this in terms of these three, that in terms of these three, and then so forth, keep going step by step. It's very easy to program. Does it work? Well, first, it's obviously consistent. Now we're going to define truncation error exactly the same as in Chapter 1. The truncation error is the residual that results when you plug in the exact solution into the approximate finite difference equation. And if you do that and use Taylor series, even though u is a function of two variables, it's really just ordinary Taylor series because in each case only one variable is changing. So the left-hand side you expand u of xi tk plus 1 in terms of u of xi tk. Anyway, you get exactly what you would expect, that it's first order in time and second order in space. This requires a little bit of work, but that's exactly what you would expect for the truncation error. It's the amount by which the exact solution, little u, the solution of the partial differential equation, fails to satisfy the approximate equation. We get the delta t term from this approximation and the delta x squared term from this approximation. Okay, so we've used the obvious explicit finite difference approximation to the heat equation, and it's of course consistent. Truncation error goes to 0 as delta t and delta x go to 0. So again, consistency is pretty easy unless you do something stupid. Unless you just use an incorrect approximation for one of the derivatives, you're going to get a consistent method. Stability is another matter. In this chapter, with all time-dependent partial differential equations, stability for finite difference approximations is very important because methods can be unstable that look perfectly fine. Consistency is easy. Stability requires more work. We're going to find lots of really innocent-looking, reasonable-looking finite difference approximations turn out to be completely unstable. So how do we test for stability? Well, in the book, there's one approach that's given, a rather direct approach that actually proves that if this criteria here is satisfied, we're going to assume now that d is constant, so that's just the constant value of d. If delta t is less than or equal to 1/2 delta x squared over d, then the explicit method is stable, and it's actually proven to be stable. That is, it's proven that the error at any given point goes to 0 as delta t and delta x go to 0. Remember, consistency means the truncation error goes to 0 as delta t and delta x go to 0. Stability means the error goes to 0 as the truncation error goes to 0. In this section, the explicit method is proved to be stable under these conditions, which means the error is proven to actually go to 0 as delta t and delta x go to 0, but only if this is satisfied. Now, this is actually a rather stringent requirement. It requires that if delta x is small, delta t has to be extremely small because it has to be proportional to delta x squared. So this is a serious stability requirement, and if it's not satisfied, the method is totally useless. In this video, I'm not going to go through the stability proof in the book because we're going to be looking at a different type of stability analysis that's more general. It works for more general problems in a minute, the Fourier stability analysis. But a little insight into why that there is such a stringent requirement on the explicit method for stability. If you look at the original heat equation and discretize x but not t, in other words, approximate the x derivatives by finite differences but leave the time derivatives continuous, then you get a system of ordinary differential equations that looks like this. And basically the explicit method is simply Euler's method applied to this system. Well, this system happens to be extremely stiff. That's proven in problem 3. It's actually a very stiff system because some of the eigenvalues are extremely large and negative. In fact, the eigenvalues are proportional to 1 over delta x squared, so the smaller delta x is, the more stiff the problem is. So for small delta x, this is an extremely stiff system, so not surprising that Euler's method only works if delta t is smaller than some threshold, and if delta t is bigger than that, it's totally useless. If it's smaller than that, it works just fine. However, it's a pretty stringent requirement. So given that we have a stiff ordinary differential equations system, it makes sense to apply not Euler's method or any explicit method, but a backward difference method. For example, backward Euler, which is the first order backward difference method. And so let's try that, and that results in what we're going to call the implicit method, which is this. Notice the left-hand side is the same as for the explicit method. The difference is on the right-hand side, all of the t's are tk plus 1's, not tk, and it's implicit because there are several u at the tk plus 1 level, so you simply can't solve this for uxi tk plus 1. In fact, you end up with a tridiagonal system to solve every step. Remember, a ODE system, if you use an implicit method, that's even more problematic than a single ODE using an implicit method, because there you have to actually solve a system of linear or nonlinear equations, in this case linear, every time step. And that's what we have to do here. See, if we put all the k plus 1 levels that we're going forward in time, we know all the u's at tk, put those on the right hand side, but we don't know the u's at tk plus 1. We have to solve a tridiagonal linear system every step. That's a bit of a pain in the neck, but it's not that serious numerically because solving a tridiagonal system is still only order n work. Now when we go through the similar stability analysis in the book for the implicit method, we find that it's unconditionally stable, which is again not surprising because basically we're using a backward Euler, first order backward difference method for solving that stiff ODE system, and we know that with the backward difference implicit methods you can take large step size with no problem. So the implicit method has the disadvantage that it's implicit, which means you have to solve a tridiagonal system every step, but it's unconditionally stable. You can take much larger time steps. Then there's another method that's commonly used for the heat equation. That's called the Crank-Nicholson method. That's basically the second order Adams-Moulton corrector formula applied to this ODE system, and it's basically just an average between the implicit and explicit method. And let's look at the Crank-Nicholson method and do a Fourier stability analysis on it, which can also be done to the implicit or explicit methods, and it's more general than the methods used in Chapter 2. So here's the Crank-Nicholson method. We're only going to apply it to u sub t equals d uxx, where we assume d is constant, and by the way, diffusion coefficient is always positive. If it's negative, the heat equation is itself unstable, so d is always positive. The lower order terms never affect stability anyway, so it doesn't hurt to just look at the higher order terms. So we'll look at Crank-Nicholson method, which, as I said, is just an average between the implicit method and the explicit method. In other words, if you remove this term and remove that 2, you just have the usual explicit method. If you remove this term and get rid of that 2, you have the usual implicit method. Crank-Nicholson just takes the average of the 2. It has a truncation error that's order delta t squared, which seems intuitively reasonable. In any case, it has a higher order truncation error than either the implicit or explicit methods. It's order delta x squared and delta t squared. But how do we analyze the stability? And the method we're going to use can also be used and is in Appendix B. It's actually only introduced in Appendix B. It's used to analyze the stability of the explicit and implicit method and a whole lot of other methods. You're going to be doing some in the homework. So this is our most important tool in chapters 2 and 3 for time-dependent problems for analyzing stability of finite difference methods for time-dependent problems. And stability is very important because it's not at all obvious. Okay, so this is the Crank-Nicholson method. Now, what is the Fourier stability analysis? Basically, we take the discrete solution. Actually, in Appendix B, the Fourier stability analysis is justified on a much more rigorous basis. It's actually shown why a method is stable. In other words, that the error actually goes to 0 as the truncation error goes to 0. Here we're just going to give you a practical introduction on how to actually implement the method without trying to justify it too much. So in practice, here's the way you apply the Fourier series method. You expand your approximate solution u of xi tk in a Fourier series where for each k you have a Fourier series, but the coefficients depend on tk. They change every time step. For any fixed time step, u is just expanded in a Fourier series, but the coefficients in this Fourier series change with the time step. So basically, we plug this in. We plug in this series expansion for u. There's no point in plugging in the whole series. We just take a typical term in the series and plug it in. And the analysis is very similar for all problems, so follow carefully here. We plug in u at xi tk plus 1, and we get this, xi tk plus 1. Then we have u xi tk. Well, there's the xi, there's tk. I usually don't even write the m there, it's just understood. And then here we have ui plus 1 tk, see tk I plus 1, ui tk, there's your tk xi, ui minus 1 tk, there's your tk xi minus 1, and so forth. And here's u tk plus 1, xi plus 1, so forth. Now, we factor out, on the left-hand side, factor out e to the im xi. By the way, the capital I represents the imaginary number square root of minus 1. I used capital I because the little I is the subscript of x. So capital I is square root of minus 1. So on the left-hand side, we factor out the e to the im xi, and we write xi plus 1 as xi plus delta x, xi minus 1 as xi minus delta x, all the way through. Factor out, see these three terms have a of tk, these three have a tk plus 1, so we factor out the a tk plus 1 here and a tk there. And now, as we always do, we cancel through, divide through by e to the im xi, so that term disappears. Here we have e to the im xi times e to the im delta x. The e to the im xi cancels, just leaves the e to the im delta x, so forth. So the e to the im xi is canceled all the way through, all 6 terms on the right-hand side, both terms on the left-hand side. And now the numerators here have the same numerator here and here. We're going to use a little trig identity. First of all, Euler's formula, which says e to the im delta x plus e to the minus im delta x is 2 cosine m delta x. And then we use a trig identity you're probably not familiar with, have to look up to write that as minus 4 sine square of m delta x over 2. So this identity here you're going to use every time you use the Fourier analysis, at least every time that there's a second order derivative involved. So this, when you might want to write that down, you're going to be using that almost every time, this same identity. Now, so the numerators here and here can be written as minus 4 sine square of something, multiplying by delta t and combining a bunch of terms. We end up with am of tk plus 1 minus am of tk equals minus r am of tk minus r am tk plus 1, where r is this. Notice that r is greater than or equal to 0 because d and delta t and delta x and sine square are all greater than or equal to 0. So r is guaranteed to be non-negative. Now taking the right-hand side on the left side, we get this. Now, what have we done here? We've expanded u in a Fourier series where the coefficients am depend on time, and we're basically looking at a typical one of these coefficients to see what happens to it. Well, we end up now with a first-order linear constant coefficient homogeneous recurrence relation. The r's depend on m, the coefficients depend on m, but for each fixed m, we're just looking at one at a time. Look at one of these coefficients for fixed m. What happens to am as time increases, as k increases? That's what we want to know. What happened to these coefficients in the Fourier series expansion for fixed m? And we get a recurrence relation with constant coefficients. For fixed m, they're constant anyway. And so we simply, as in chapter 1, we know that constant coefficient homogeneous linear recurrence relations can be solved with exponentials, lambda to the kth power. Plug that in and we get our characteristic polynomial, and it has this first order characteristic polynomial, so only has one root, 1 minus r over 1 plus r. R is non-negative, therefore the numerator is always smaller than the denominator in absolute value, so the lambda is always less than or equal to 1 for all m. So for each m, the am has the form lambda to the k, where lambda is less than or equal to 1, therefore it doesn't grow. Now, as I said in Appendix B, a more rigorous proof of stability is given from the Fourier analysis, but at least here you can see that if any of the roots for any m were bigger than 1 in absolute value, if any of these roots for any m had been bigger than 1 in absolute value, then the corresponding coefficient would grow exponentially, and the method clearly is unstable, just like in chapter 1. So for stability, you need that for all m, all roots, in this case there's only one because it's first order recurrence relation, but in some of your problems it'll be second order, involve 3 time levels or more, and you'll have a second order recurrence relation, and you'll have 2 roots for each m. In this case we only have 1, but all roots for all m have to be less than or equal to 1 in absolute value, or the method is unstable. If they are all less than 1 in absolute value, the method is stable. Now, a method, as we know already, can either be always stable always unstable or conditionally stable, like the explicit method will be stable if delta t satisfies a certain criterion that we found. The implicit method and Crank-Nicholson method we now see are always stable. In other words, they're stable no matter what delta t and delta x are. Okay, now we look at a numerical example. Ut equals uxx, so d is 1, plus we have lower order terms, but as I've commented, the lower order terms do not have any effect on stability at all, so it's the same as if it were just ut equals uxx as far as stability is concerned. We have a little bit different boundary condition on the right-hand side, but still one boundary condition on the left side, one on the right, and one at the bottom, that is for t equals 0. And let's look at the results on page 76. First, we apply the usual explicit method, that is, we're applying Euler's method to solve the system of ODEs. And if you look at the stability criteria, it says that delta t has to be less than or equal to 1/2 delta x squared. If delta t is exactly 1/2 delta x squared, the method works fine. If it's very slightly more, so this is only a very slight increase there, and still very small delta t compared to delta x, this barely violates the stability criteria for the explicit method, and you see you get instability. On the other hand, if we use a first order backwards difference method, that is the backward Euler method, that is the implicit method, now we can use much larger time steps and it still is stable. Then we also used a fourth order backward difference method, which is also unconditionally stable. All the backward difference methods are good for stiff systems. And here, when we use a large delta t, we get much better results because it's fourth order in time. In the next section, we talk about multidimensional problems, that is, where there's more than one space variable. For example, here's a heat equation in a two-dimensional region, ut equals duxx plus duyy plus possibly some source term here. Again, d is the diffusion or heat conduction coefficient, but now u is a function of time and x and y, so now we're talking about heat conduction in a plate. And we're going to give the temperature on all four sides of the square for all time, and the initial temperature in the entire plate. Those are the appropriate initial conditions for this method. Again, we can use implicit or explicit. Here's the usual explicit method for approximating that. There's the Euler approximation to use of t. Here's the usual approximations to this is B, approximation to uxx, approximation to uyy. They're all at level t, so it's a explicit method. That is, you can solve for uxi, yj, tk plus 1 in terms of values of u on the previous time level, and then you can go step by step, time level by time level. Don't need to solve any linear system, but as you might expect, there's a stability problem. Delta t has to be less than something fairly small to avoid instability. Truncation error is defined the same way as before. Truncation error, as you would expect, turns out to be proportional to delta t and delta x squared and delta y squared, so it is consistent. Then we do a stability analysis and find that it's stable if and only if delta t satisfies this condition here, well, assuming delta x and delta y are the same. It's almost the same condition as we had for the one-dimensional case. And of course, you can also use implicit method. Now, the thing to notice here is if you use an implicit method, such as the backwards difference method, first order backward, any backward difference method, or Crank-Nicholson, implicitness, you pay a higher price now, because now you not only have to solve a linear system, but the linear system is no longer tridiagonal. It's banded, and you can use a band solver, but it takes a lot more work. So every time step is expensive for the implicit method, but it has the advantage of being always stable. Finally, we have an example. This is a system of two diffusion equations. So there are two unknown functions. They're both functions of x, y, and t. We have the following boundary conditions on u and v in the square, and have initial conditions that u and v both start out to be 1. Notice these are nonlinear. We're going to use an explicit method, despite the fact that you have to be careful with the time step with the explicit methods, because those are so much easier to program than the implicit methods. With the implicit method, you see you'd actually have a nonlinear system, large nonlinear system to solve every time step because it's a nonlinear problem. So that would be much more difficult to program. But using the explicit method is really easy to program. Here are the finite difference equation, the usual Euler approximation on the left-hand sides, and the usual second order difference approximations to the second derivatives. Here's the program. Extremely simple. Because it's explicit, you can just march forward in time. Every time step, you simply calculate the new uij and the new vij at the new time level. It's explicit. All of this is at the kth time level. So that's the entire program. And the results are good, but you have to keep the time step small. If you don't, in fact, we tried it, if you make delta t slightly larger than the stability requirement, the method blows up.